This is arguably the most important video that I'm going to show you all semester, and it's primarily due to the fact that the topic that we're going to discuss right now, integration in a proton NMR, is one that has enormous value, but because it's relatively difficult to get your head wrapped around and it's difficult to perform integration on real spectra, students tend not to use it as much as they should. I have generated a video series on NMR that I have filmed and uploaded and put on YouTube, and one of the key videos that I've made is one that really goes through why students get hung up. But the key idea is that students don't rely on integration enough, and professional organic chemists rely on integration very much. Whereas, by contrast, students find multiplicity relatively straightforward, and therefore they rely on it much too much. And professionals recognize that that will lead you astray, so they tend not to do it. If you want to know more, go watch that video. So the key thing I want you to know right now is that integration are the blue numbers at the bottom of the spectra, and once you have a good set of integrals, what those numbers correlate to is the number of hydrogens in each one of these environments. So if we call this group of lines a peak, then what this is telling you is that there is one hydrogen in this environment relative to two hydrogens in this environment, one hydrogen in this environment, three hydrogens in this environment, and six hydrogens in that environment. Why am I ignoring the fractions involved in all of these? Well, because there's no meaning to a fractional number of protons. If you are thinking about a single molecule, it has a certain number of hydrogens in each environment, and that's it. It's going to be integers. It's going to be 1, 2, 3, 4. It can't be fractional numbers. But one thing that makes integration tricky in NMR is because you actually have to define those integrals in the first place. And what I'm doing by clicking and dragging across these peaks is I'm defining the region that counts for the purposes of the integration of the integral. So to back up just a step, I think that one of the main problems students have with the idea of integration is that they don't have the necessary understanding from calculus that integral, generally speaking, means area under the curve for people who are not interested in math for its own sake. Ask a mathematician to define integration for you, and they will go into a relatively long, drawn-out explanation. And if you asked instead a pharmacologist or an organic chemist what an integral means, we will respond with area under the curve. What that means is simply amount of stuff bounded by some curve. Specifically, in the context of NMR, what that means is the number of hydrogens occupying a given environment. But what makes things difficult in trying to perform integration is that you have to do interpretation of the numbers that result. So I've now shown you a blank spectrum with no integrals. I've shown you a spectrum that's been integrated well. But if I just simply come over here and perform an integration of some peak generically, whatever peak I integrate first is going to be 1 in this spectrum. Why? Because that's what the computer decides. If, however, this peak is integrating for 1, that does not mean it's worth 1 proton, because if I now integrate this peak over here, you will see that it is small. And so, okay, relative to this has twice the amount of stuff under the curve, and so perhaps what you should do is call this 1 proton in this environment and 2 protons in that environment. And that would make a certain amount of sense, except that there's a smaller doublet here as well, and now you see, wait a minute, this is the smallest of the peaks, so maybe this is worth 1, and then maybe this is worth 2, and then maybe this is worth 3, except that if you try to work that out, it won't work either. And so you have to do even more interpretation and even more thinking. And as it turns out, if you integrate this as the smallest possible peak, then maybe you'll start to realize what's going on here. If you simply highlight this curve so that the pink lights up red, and we go to edit integral, we can now set that normalized integral to be 1, and now you will see something that will make quite a bit more sense. If this is 1 proton, this is 2 protons, this is 3 protons, and this is 6 protons. But ultimately, if there's a single concept I want you to lock away right now, it is that an integral, for a chemist, refers to the area under a curve. That's why we care about integration. It is us using a tool from calculus 2 specifically at HWS, that allows us to extract valuable information. So if you have some curve, we are interested in the area under the curve because that will represent something real and physical physical. And in the context of NMR specifically, what that represents is the number of hydrogens in a given environment, the number of hydrogens in a given peak. But again, it all comes back to this is an area under a curve. In the modern day and age, if I want to approximate the area under this curve, what I would do instead of cutting it out is just simply approximate it by a series of rectangles, each of which gets more and more precise as we go smaller. Now, in practice, of course, I'm doing absolutely none of this. However, that's what any computer program is doing to figure out the area under this curve. So right now, what a computer program is doing is using really, really small slices, almost continuous slices of various boxes, and that's what this little curve showed you. At the end of this animation, what we ended up with is 64 individual rectangles, but you can tell that there's a little bit of a poor estimation there. But if you went to finer and finer slices, you would end up doing a better job of approximating that area under the curve. The key idea here, of course, is that this curve is poorly represented by just taking the area of this square. This rectangle has an area of 8, but you can clearly see that this is somewhat less than half of the area of this rectangle, and you really have to guess as to what that is. Or you can break it up into two smaller rectangles. This rectangle has an area of 1. This rectangle, of course, has an area of 4. And now you see that this is probably a bit over half of that rectangle and a bit less than half of this rectangle. So we are making a better estimation of what this curve looks like. But it will get better still if we go to finer and finer and finer slices until eventually we end up with a pretty good approximation. You will notice that there is relatively less leftover blue area that does not represent the area under the curve if we are using these kind of finer and finer slices. So any computer program is simply running this process just using thinner and thinner slices, and that is, for one definition, kind of what calculus is. Taking infinitesimally small slices to describe what's going on in a curve. To demonstrate the idea that this really does represent just an area under a curve, what I'm about to show you is the fact that I just have physical pieces of paper here, and this is a image of that spectrum already drawn out. But what I've now done is zoom in on each of these peaks in turn, so that I have them printed out all on the same scale on various pieces of paper. And what I will end up doing is cutting all of these pieces of paper out and then weighing them for you so you can see that this is in fact what the peak integration represents. The area under the curve, which in this case is the mass of the paper underneath the curve. This might strike you as strange, but before computers were a significant thing that we used all the time, this was something that you actually had to do. I personally have cut paper out and weighed it to determine the area under a curve. Be grateful that we no longer have to do that. It should hopefully be obvious, just looking at the various peaks here, that the quartet and the nonet integrate for the least and have the smallest amount of paper involved, whereas the doublets are all larger than that. And then, of course, it should be obvious which of the doublets should have the highest mass, because the area under the curve is largest, the peak is physically largest. But in particular, looking at the doublets, it should be clear which one integrates for 2, which one integrates for 3, and which one integrates for 6. We will now weigh each of the peaks in turn just to see how much mass is involved in the paper. The quartet on the weighing pan weighs 16.5 milligrams, 16.6. The nonet on the weigh pan is weighing 22 milligrams. The doublet worth 2 on the weighing pan weighs 34.3 milligrams. The doublet worth 3 on the weigh pan weighs 51.1 milligrams. The doublet worth 6 on the weigh pan weighs 106.2 milligrams. I had to take some particular precautions to ensure that the results were as good as the ones that you saw. The most important of those was to print each peak on a consistent set of axes. So the same intensity axis for the y-axis and the same width in terms of chemical shift on the x-axis. In addition, I had to ensure that I had drawn a good baseline underneath each peak, and then to use an X-Acto knife to cut out the actual peak itself, trying to be consistent with the amount of paper paper that I had left over on either side. That last factor becomes relevant and is probably best illustrated with this quartet peak here, wherein in the middle I had a sufficient amount of paper so that I could in fact cut along the line if I wanted to, but along the sides what I discovered is that the line essentially disappears altogether. And so I decided that I would try to ensure having a little bit excess paper on those sides. And then here in the middle I didn't quite hit the line that I wanted, but again, it's super challenging because I wanted to make sure that I didn't cut the peak off. Likewise with this peak, which appears to be a septet when I cut it out, because you cannot distinguish the nonet part from the baseline unless you increase the intensity dramatically. So if you look at this on screen, it's an actual nonet. Here is the peak as printed. Here is the peak when zoomed in high enough. And what you can tell if you measure distances relatively precisely is that the distance from here to that peak is 6.7 hertz, and the distance from here to the top of that peak is likewise about 6.7, 6.8 hertz. What that suggests, especially because this is symmetrical and I could perform the same analysis on both sides, is that this peak is truly a nonet and not a septet as it appears. When printed out, of course, you cannot distinguish the nonet portions from the baseline meaningfully. You can barely see that they are there if you are looking extremely carefully, but when printed, that is not a deviation that's able to be seen. When attempting to cut out the nonet, it is not even possible to distinguish the nonet parts in the paper, so I reduced it to a septet, but then I had to have some non-zero paper on both sides in order to cut this part out. And this, by the way, is a meaningful finding. If you look at the level of intensity with which I've zoomed in, you can now see deviations in the baseline, and when you are integrating this entire peak, we are integrating some of that noise, and that will have a tendency to disturb the integral of this peak. By contrast, with the doublet, there is no such requirement to have excess paper on the peak, and therefore it is easier to compare all three doublets to each other. The amount of deviation from the baseline is more consistent with the doublet peaks relative to each other. And this is an important finding. When I'm doing the integration by paper, I can clearly have the doublets integrate on a consistent scale relative to each other, and that's actually a finding that translates into the computer as well. If you want to compare integrals, ideally they have the same peak shape, because peaks with different peak shape will include various amounts of the baseline into the integration, both for better and for worse, depending on whether the baseline is deviating high or deviating low in that area. The message is that you can be much more precise with your integrals in a case where you are comparing peak shapes that are identical, but as soon as you start comparing peak shapes that are different from each other, what you'll find is greater deviations than you might expect. But the truly global message in this entire video is that integration represents the area under the curve. And though that is best measured by a bit of calculus and employing computer technology, it is possible, and in the old days I have actually done it on purpose for a real measurement, to print out onto some relatively uniform piece of paper and then to cut out the peak in question or the curve in question in order to determine the integral by mass. The area under the curve is simply the amount of stuff represented by that curve, and the amount of stuff in the context of NMR then represents a number of protons in that environment.